Hi, Algebra 2 students. This video is on properties of logarithms. And we've seen some properties of logarithms in class already, and I'm going to introduce some more, and then we're going to show you how we can use properties of logarithms to both expand and condense expressions. So first of all, I just want to kind of keep in mind, we're going to say recall our definition of a logarithm to be log base b of x equals L. That this notation is equivalent to saying b to the L power is x. I want to keep that in mind. So now what we're going to do is create a little chart. So we're going to list out the properties in one column, and then the second column is going to be for examples. So I'm going to split my page in half. Okay, so my first property is one that we've seen and you guys have actually understood pretty well, is that log base b of 1. So no matter what your base is, if it's base b of the number 1, it will always equal 0 because any number to the 0 power is equal to 1. So just a quick basic example, if I have log base 8 of 1, 8 to what power is 1? The answer would be 0. The next property is log base b of b. So if you think about it, we're saying b to what power that I'm going to write here is b. Well, b to the first power is b. So no matter what this b is, if you see the same number there, your answer is just going to be 1. So something like log base 2 of 2. That will just be 1. The next one, which we saw in class today, was log base b of b to the n. We saw this with log of 10 to the k power, something like that. So the idea is, this was, if I'm saying b to what power I write here is equal to b to the n, well, this would have to be n, because b to the nth power is equal to b to the n. So an example would be something like log of 10 to the 7th. Remember, if you don't see a number down here, it's log base 10. So this must be equal to 7, because this is saying 10 to what power is 10 to the 7th? Well, 10 to the 7th power is equal to 10 to the 7th. So for the next property, it actually has a name, and it's called the product property, and it's the one we figured out in class. Product property. So remember, product means multiplication. So the idea is that we say, we have log base b of x times y, that is equivalent to, you saw it was equivalent to the sum of the log of each factor. So log base b of x plus log base b of y. And an example would be something like log of 15. So I know that 15 is 3 times 5, so this should be equivalent to log of 3 plus log of 5. And now the next one is kind of like a special situation of this one, so it's kind of like a subcase. We'll say special case. And this is log of 10 to the k power times x will always equal k plus log x. And this should make sense because, like, if you just think about splitting the two, and it would become log of 10 to the k plus log of x. Well, what if you ignore that x for a moment and think, what is log of 10 to the k? It's just k. So this first chunk log just becomes that k out front plus the log of x. And our example there will be log of 500. So I know that 500 can be written as 5 times 100, right? And 100 is really 10 squared. So that means I can split this into log of 10 squared times 5. And if I can do that, that means that this 2 kind of comes out, right? And I have 2 plus log of 5. Okay? And then let's look at the next property I'm going to introduce is something called the quotient property. And the idea of the quotient property is quotient, remember, means division. So if we have log base b of x divided by y, it's going to be similar to the product, except instead of a sum here, we're going to end up with a difference. It's also similar to our exponent rules. So we have log base b of x minus log base b of y. And an example would look something like log base 4 of 2 over 3. That should be equivalent to log of the numerator minus log of the denominator. Okay, we have one more property to write down. The last property is called the power property, and we also looked at a case of this today in class. The power property says log base b of x to the k, so x to some power, will always equal, you can bring that power out front and write k times log base b of x. So an example would be log base 5 of 7 to the 6th power. That's going to be equivalent to, bring the 6 out front, log base 5 of just 7. Okay, so now that we have all of these properties written down, we're going to look at some examples. We're going to kind of have examples in sets. So we're going to say like example set number 1. These are all going to be using tables. So that would be similar to what we were doing in class today, where we had a chart and we were kind of using the values in the chart to determine specific values of the logarithm. So if we have my first example, log of 2100. And we're going to try to do this using the same table we were using in class. So I'm just going to, I have this table printed out. So this is the one that you guys created in exercise 1 in your workbooks in lesson 11. So if I see the values I have here, so I have the numbers 1 through 9, I have some other powers as well. Well, I want to try to split 2100. Well, if I can get some powers of 10 out of that, that's helpful. So I know like I see the 2 zeros means this is 100 times 21, right? And then 100 is 10 to the 2nd power. So I can think about this as log of 10 squared times 21. And now 21 is still not in my table, but I know 21 is 3 times 7, and those are both numbers in my table. So now I know this should split into log of 10 squared plus log of 3 plus log of 7. Log of 10 squared. Well, I remember this is base 10, so this just becomes the exponent because 10 to what power is 10 to the 2nd? 2. 10 to the 2nd power is 10 to the 2nd. Plus, I would look at my table to get the value for 3, log 3, and we see that it is 0.4771, and then log 7 would be 0.8451. So now at this point, I'm using squiggly equal sign because these are both approximations. So from here, I would just type this into my calculator to get the sum of them. And this should come out to be 3.3222. And that would be my answer. So there are problems like this in your homework. Okay? So next up, let's look at another example. We have log of 0.00049. So this looks crazy, and I'm thinking, how can I use just these whole numbers in this table to figure out this small decimal? Well, remember that all those zeros are really multiplying by like a negative exponent of 10. So to figure out what it is, you can kind of go backwards, 1, 2, 3, and I like to go all the way to the end so I get like the whole number of 49. So that's 1, 2, 3, 4, 5. Because 49 I know I can break down into numbers on this table. So then from here, I could write this as log of, well, since I moved it over 5 decimal spaces to the right, this is kind of like scientific notation, except I went all the way to the whole number. I would do 10 to the negative 5 times the 49 to get me to this decimal. Okay, and then I know 49 is 7 times 7. So from here, I now know the splits into log of 10 to the negative 5 plus log of 7 plus another log of 7. And from here, I know that log of 10 to the negative 5 is just negative 5. And based on my table, I know log of 7 is 0.8451. We got 2 of those. You could also do times 2 if you don't like writing this out twice. And this is, again, an approximation. So then I get, if you punch this into your calculator, you get negative 3.3098. All right, I have one more example for you in this set of examples, and that is log of 1 over 15. Okay, and the trick with this one, there is no 1/15 in my chart, right? But there is a 3 and a 5 which multiply to 15. So the idea here is I could say this is equal to, well, I could bring it out of the fraction by raising 15 to the negative 1 power, right? And then I know that I have the power rule which says, or power property, which is that negative 1 can come out front. So now I have my answer should just be negative 1 times whatever log of 15 is, and I know 15 is 3 times 5. So this should equal negative 1 times log 3 plus log 5. Log 3, again, is, so at this point I'm approximating, 0.4771 plus log 5 is 0.699. If I punch that into my calculator now, so let me slide my paper over. This is going to become negative 1.1761. Okay, so let's move on now to our next set of examples. So these were similar to what you're going to do in your homework. What we do next is going to be a little bit different, but it's going to be kind of where we're headed next time I see you. So I want to kind of preview the other types of problems that we're going to be practicing later. So example set number 2, we're going to be expanding logarithms. So my first example is log base 2 of 3x to the 4th times y. Okay? So if I'm expanding, I want to kind of pull it apart. So it's currently a product of 3 things, of 3x to the 4th and y. So if I pull that apart using the product rule, it should be log base 2 of 3 plus log base 2 of x to the 4th plus log base 2 of y, right? There's one other thing I can do here to completely expand this, which is that I have an exponent with my x squared. Well, I know whenever I have an exponent, it can come out front. So this would just become 4 log 2 of x. And I'm going to bring down the other 2 terms so they don't change because they did not have an exponent. Oops. Okay. So then this would be this thing expanded. That would be our expansion. You can see that it got bigger. Okay, the next one we have is log of a squared times b over c. So first of all, I see that I have a quotient or division, right? So I know that when I have division, it's going to be the subtraction of those two. So it would be log of a squared b minus log of c. And from here, I can still do more because this is multiplication, right? So, and I also have an exponent, right? So I know my exponent can come out front of my a log, right? And I'm also going to do the sum of a and b, pulling that apart. So I'm going to do that, try to do that 2 steps in one. So the 2 is going to come out front of log a, because it was the exponent of a, plus log b. And then I still need to bring down that minus log c. So this would be the complete expanded form here. For the next one, we have log base 5 of p over q squared r to the third. So again, I have a quotient, so I'm going to pull apart the quotient first, which would be log base 5 of p minus the denominator, log base 5 of q squared r to the third. But now I'm going to kind of treat this separately. This is a product, so it should become a sum, but they still will have that negative sign out front. I'm going to bring down the log base 5 of p, bring down the minus, and I'm going to put parentheses and break this apart. So I know my exponent will come out front. So the q squared becomes 2 times log base 5 of q. That 2 just got moved out front. And then plus 3 log base 5 of r. The 3 was the exponent right there, so that came out front and the r was left over. Okay? So we could leave our answer like this, or we could distribute that negative in to just be a little more precise. So then we would get log base 5 of p minus 2 log 5 of q minus 3 log 5 of r. That would be the completed answer. Okay, so again, this process is called expanding logarithms because if you notice, what we started with is a lot smaller, more condensed than what we ended up with the sum. So we're going to think of our condensed version as being a product or a quotient, and then our expanded form as being the sum or the difference. Okay, so one more set of examples to look at. Only three more. And this is going to be condensing now. So going from like the addition or the sum or difference to the multiplication and division. So my first example here is log 3 of 5 plus 2 log 3 of x minus 6 log 3 of z. So to start, I'm going to deal with the numbers out front because I know that they should then become my exponents. So if I just first start by that, I'm going to have log 3 of 5 plus log 3 of x squared. That 2 just got moved up to be my exponent with the x, minus log 3 of z to the 6th. Because there was a 6 out front, that got moved up. Okay, so from here, what I'm now going to do is, okay, so I see a plus sign. That's telling me to multiply 5 and x squared together inside of my log. Right, so this will become 5x squared on top. But then the minus is telling me to divide that by z to the 6th. So I end up with log base 3 of 5x squared divided by z to the 6th. And that would be my nice condensed small form. Okay, let me slide this up. The next one is 2 log a minus log b minus 3 log c. So again, we're going to start by dealing with the numbers we see up front by making them our exponents. So this would become log a squared minus log of b, that doesn't have any exponents, minus log of c to the 3rd. So that 3 becomes my exponent up there. Okay. So now what do I do? I have to think about what I have two subtraction signs. So that's like dividing twice, which might kind of hurt your brain to think about. But we could also kind of just factor out a negative sign and treat this as log b plus log c to the third and bring down the log a squared. So just kind of follow what I did. I saw two negatives, so I factored out a negative and wrote this as a sum. That allows me to more easily see what I need to do now, because I now see I have log of a squared minus this thing. So I know I'm going to do log of my numerator should be a squared, and my denominator should be the log b plus log c cubed. But I remember that adding to means multiply. So it would be b times c to the third. And that would be my final answer. So to recap, we factored out the negative and we saw two subtraction signs. That turned this into a product of b and c to the third, but then since it was being subtracted, it went on the bottom, and the a squared stayed on top. Okay, one final example. We have 2 times the quantity log 4 of 6 minus log 4 of 3 plus 0.5 log 4 of 25. So this looks kind of crazy. I'm going to deal with this 2. I'm going to deal with always the numbers out front first. So that 2 means it would become an exponent of 2 and get distributed into both things here. So that would look like log 4 of this exponent will go to the 6 and become 6 squared, which is 36, minus log 4 of 3 squared, which is 9. Plus, now to deal with this exponent, 25 to the 0.5 power, that's like 25 to the 1/2, which is like a square root. So this becomes log base 4 of the square root of 25, which is 5. So we were able to kind of simplify that pretty nicely. So from here I know the subtraction sign means to divide. So I'm going to do log base 4 of 36 over 9. Plus log 4 of 5. Well, now I can actually simplify 36 over 9. It's just 4. So this becomes log base 4 of 4, which is one of our properties, because we say log base b of b is equal to 1 because 4 to the first power is 4, right? So this is just going to become then kind of like our final answer would be, I just replace this one with a 1 plus log base 4 of 5. Okay, and that would be our final answer. So again, we're going to be practicing expanding and condensing next class, and do the best that you can on the homework, and we'll be sure to talk about it on Friday.